So today my topic is closing the Sim2Real gap with physically accurate SimReady assets and benchmark. So I think so I will show something that's probably a little bit different than what the other speakers are sharing. So it's more of industry approach, right? How we as I would say the most leading synthetic data and also simulation provider for physical AI, especially for robotics, how we are approaching this digital twin problem. Yeah, so I think I already gave the introduction of me, so I will skip this part. And also a very quick introduction of LiveView. So we are a simulation synthetic data provider for physical AI. So we serve quite a lot of really great clients, right? And it basically, so for example, the customers working on the robotics foundation model or even the world model, for example, NVIDIA, DeepMind, ByteDance, right? And also the leading, I would say, educational institutions such as Stanford, MIT. And also the other part is, the leading embodied AI robotics companies, for example, Figure, AGI Bot, Galbot, Genesis. And also, we also serve some of the more, I would say, industrialized companies, for example, Bosch, Toyota, Li Auto, BYD, right? So basically, you can see on the left-hand side, we serve quite a few different set of products there. The first one is the SimReady asset, which I will go over by detail. And then with the SimReady asset, since the digital twins, we are generating large amount of synthetic data, and actually the largest amount in the whole world right now. So I will give you a very quick tour of that. And then also providing our simulation platform to enable, the world model and also foundation model providers to fine-tune their vision language action or vision language models. Cool. And before I get into the detail, I just want to say that, I'm a strong believer of, the data pyramid concept. And as I was previously from the self-driving background, right? The more I'm working on robotics, the more I'm working on embodied AI, the more I really see that, the direction of the robotics foundation model it is more towards, a combination of real data, synthetic data, web data, and also human videos. So it's a combination of all types of data, rather than just one type of data. The other thing there is, the more I'm working in this direction, the more I really see a huge growing demand from our customers on synthetic data, and the more strong conviction that I really fully convicted that synthetic data is going to be probably the most major source of data to power up, the foundation model of physical AI. Cool. And I'll first get into the SimReady asset part. So I really see that the SimReady assets are the foundation of digital twins for physical AI. So basically a few of my understanding here. So first, I would say by digital twin here, I also include a digital cousin, which is concept by Fei Fei. And for the SimReady assets, basically meaning the asset itself is ready for physically accurate robotic simulation. So it's not only an asset for gaming, it's not only an asset that is visually accurate, but most importantly, it is an asset that is physically accurate. And also, I will give more introductions of it not only needs to be visually accurate, physically accurate, but also it needs to support very large parallelizable reinforcement learning. So I will first go over a few very quick examples here. So you can see for this fridge, the fridge is not only visually accurate, most importantly, it is physically accurate, meaning that basically it has the hinge, it has the joints, it has a physical mechanism. It has even the magnetic force that when you are pulling like the door, like there is the magnetic force of it. And also there is the multi-friction of the drawer. Cool. And so for this side, this is a digital twin of 7-Eleven grocery store, right? And the most important thing is not that it is visually accurate, but mostly importantly physically accurate. You see, there is a hanger, right? And there is a hole in each of those items, and you can pull the item off. So the friction, the weight, and all the other things are very accurate. And this can be run in ICCV, right, as a real-time simulation that can support large-scale data collection, but also it can support large-scale parallelizable reinforcement learning. So meaning that we can run thousands of environments in parallel on one GPU for this thing. And this is a benchmark that we recently refreshed. We are a fan of open source, very influential robotics benchmarks, right? And personally, I am a very big fan of YCB. So YCB, I would say, it may not be a benchmark in the sense that it doesn't define tasks. It mainly defines the assets there. But still, YCB is a benchmark that it has the real asset. It also has the sim asset. But the major problem before is previously the sim model wasn't accurate, and it was mainly visually relatively accurate, but it didn't have any physics. For example, it didn't have the mesh. It didn't have the physical parameters, right? It wasn't it couldn't simulate the articulated assets there, right? And also it couldn't support very well for the major physically for the major physics simulators, for example, ICCV and also Majorco. So this is so this was YCB before. And this is the level YCB on the right-hand side. So you can see that we have done a major refresh, that it is not only visually accurate, but also it has the mesh, very accurate mesh, very accurate collision, right? And for each of those items there, we have run the human-based teleoperation in simulation to just do the quality control. And also we can even simulate the deformables, for example, the cloth. And for the major assets there, we support all the articulation. And also not only supporting SISIM, but also Majorco. Cool. So this is just some example of what we are doing for the the SimReady, the ISS. And then it also depends on the simulator we are using, right? For example, for deformables, a lot of people are maybe arguing that it is very difficult to fold cloth in simulation. Well, it was, but now it isn't. In that we are working very closely with NVIDIA, especially with their ICCV Newton team, right? Not only working on the SimReady assets for the existing simulator, which is physics engine, but also working on the next generation of the simulator, which is Newton. And a beautiful thing right now is, the deep down physics solver, either physics or Newton, the simulator, basically ICCV, the rendering, which is Omniverse, the on top framework, which is SILab, they're all open sourced, right? Meaning that basically it's very easy for you to leverage Warp, the GPU accelerated solver language, to write new solvers, contribute into this simulation ecosystem, right? And we not only work on the cloth simulation for here in physics in Newton, but also we work on a lot of cables. So if you see on the upper left-hand side, this is a cable in the industrial scenes there. So for this one, we actually work on our own solver, which we wrote in Warp language, contribute in Newton ecosystem plug in with ICCV SLab so that it can support data collection, it can support reinforcement learning, it can support benchmarking. Yeah, but then there is definitely more like other very interesting things. For example, being able to cut sausages, right? Being able to leverage a tool to manipulate with other things. Being able to leverage the knife in the surgeries to cut liver. And also, for example, on the bottom right, which is my favorite, which is to be able to pick strawberries. So this strawberry thing is very interesting in that the strawberry itself is deformable, right? But also it it needs to be plugged in with the stem, and also you can actually easily cut the stem, right, in order to pick up the strawberries. And this whole scene is procedurally generated, meaning that you can randomize the generation a lot. And then basically this whole scene is fully supported in not only SISIM, but also SLab, so that it can support the reinforcement learning policy training, right? We are actually training policies in this scene, in SLab, right? Through all those randomizations, procedure generations, and then supporting the policy trained from SLab, from this scene, to some of our customers to be able to handle, for example, strawberry pickup manipulation. Cool. So this is definitely more cables that I want to talk about. And it's very interesting that the more we work on cable, the more we start to realize that, this is probably one of the top use case in this whole industry that yet to be fully solved, right? By fully solve this cable situation, what I mean is, we need the deep down solver. We need a lot of SimReady SISIMs. We need very good rendering. We need definitely the data collection, right? Meaning be able to manipulate, the dex hand, the gripper, the different type of robotics to collect data. We also need to support large scale benchmarking, right? But also most importantly, we need to support large scale reinforcement learning, right? So all those things need to be plugged in together to support this cable use case. And that's something that we are already working with some of the industry leaders to solve this cable issue. And also this would often, I would say, combine with tactile sensors, because when we are dealing with, the deformables, the non-rigid body, the tactile sensor is becoming more and more important for us to measure the different type of forces, so that we can have very good real and sim benchmarks around the forces there to make this digital twin the most accurate as possible. Yeah, and also leveraging robots, leveraging the robots to close the window blinds. And this is also something that is pretty cool that I want to introduce you to, which is the home. So the home is a home of all deformable, all non-rigid body tasks with just the robots. We just want to demonstrate, to the academia, to the industry, to everyone, that what we can achieve with just simulation. And it's a really awesome thing that so my team just won the best poster in IROS for the home. And we are planning to open source all the SimReady assets, scenes, tasks of the home. Cool. So I want to quickly talk about how should we define a good SimReady assets, right? So this is again. So I think this could be relatively different than what other speakers have been talking about. About the digital twins. So what I really mean is, beyond the digital twins, we should also make them physically accurate, right? So the physics readiness part should include, marrying all the physics in real, in sim, benchmarking them to make sure that, they fully match. The teleops readiness is more like, if you build a house, if you decorate the house, right, the house most likely wouldn't be ready until you have lived in the house for 1 month, right? You have tried everything out, right? Usually, maybe some of the time the pipe is not working, the kitchen is not working, the fridge is not working, the electricity some of the time may not be fully working, right? Until you live in the house for 1 month to fully test everything out, to fully fix everything should work. Same thing as for the digital twin, for the SimReady assets there. We leverage teleoperator to teleop robots in the simulation environments to interact with all the different type of, SimReady asset scenes, just to make sure that they are fully functional. And if they are not, we will fix every problem. The third one, which I think is the most important thing, is the reinforcement learning readiness part, right? So just to give you an example, some of the time, we may have very accurate digital twin from a physical accuracy, collision, visual perspective, but it may be too complex, too large to load, right? So we need to actually care about the computational efficiency. And also a lot of the features there could be enabled in CPU, but may not be fully enabled in GPU, in different type of simulators there. So there are a lot of, I would say, problems that we need to fix in order to get the SimReady asset into the RL readiness part, which I think is the real, like a very important thing. And then basically we would benchmark, we will have the different type of physical sensors in real and in sim, right? To benchmark the real, benchmark the sim, just to make sure, for the, so for example, for the microwave, everything physically, every physical parameter wise, it would match, right? And for deformables, it's a little bit more complicated in that we need to have tactile sensors in real, in sim, right? Benchmark everything. And this is more like a generalized pipeline. So as you can see, so I wouldn't get into detail, but you can see that, we would leverage some of the generation 3D generated pipeline as our input. But then there is still this, I would say, we would call it human in the loop, but I would say largely automated pipeline to add on all the physical parameters part to make it SimReady. And after that, we would go through all the validation, right? The validation that we just showed in order to make sure that, this thing is fully SimReady. Yeah. But I would say that the digital twin is not enough. Even if we have the fully functional SimReady digital twins, it wouldn't be enough. We actually also need digital twins with tasks. So basically, we need benchmarks, right? So for example, if we have a digital twin of the factory, but if we don't have any task ready, we still cannot use it for physical AI, right? So this is actually another thing that my team just did. We are going to open source pretty soon, which is, to refresh the Libero benchmark. Libero is a really well-known and very influential benchmark. It is really great. The major problem there is not, I would say, the SS part is not SimReady, and also it didn't support the ISAC Sim, which I think is the probably the best simulator right now that we can leverage, right? So basically, we have refreshed everything to make everything SimReady from a sim, from a sim ISAC perspective, and also add on all the articulation, right? And then we enable it in ISAC Sim and also Majuco. And beyond that, we are also migrating all the tasks there. We are even collecting large amount of data. We add in a lot of different type of robotics, right? So that we have all type of robotics collecting all type of data, and we are going to open source this benchmark. Cool. So now with the benchmark with the SimReady assets, since what can we do? We can actually collect huge amount of data, right? Leveraging the different type of data collection methods there. So this is Drelo with Stanford. So this is Quest, right? With all the different type of ways we can collect data. So we would let human being to teleop into a robot through the different type of data collection solutions. And this is, I would say, one of the most exciting things that we are building, which is the world's largest synthetic data factory. So in this factory, so there are more than 250 people all collecting. So there's zero real robot in this factory, but all simulated robots, right? So 200 people collecting it every day, right? So and the data is supporting, some of the world's most leading frontier robotics foundation models right now. Cool. So a lot of people may ask, so how can you make sure that, this data can enable the Sim2Real? Actually, the answer is we are doing it ourselves, right? We are actually working with our customers, but also doing it ourselves. So I would say the most important thing is to leverage the data to do the pre-training, to do the post-training, right? And to testing the Sim2Real gap, to always do the Sim2Real, right, in the real robots, and always test the gap, so that we build an iterative cycle, right? And I would say that pre-training part may be a little bit different in that you would need a lot of compute, but I would say our customers, they have huge amount of compute. Quite a few of our customers have more than tens of thousands of GPUs just leveraging our data to train the foundation models right now, right? So we get a lot of very great feedback with them together. And we also leverage the foundation model they trained, and we would leverage the more synthetic data from our side to do the post-training, the fine-tuning, right? And then we would deploy the model on a real robot. We would do the Sim2Real ourselves. We would close the gap so that we can gather all the different type of feedback and to improve this loop. This loop would mean that the SimReady asset making part, the data collection part, and also the data mixing strategy part, the data recipe part, the data annotation part, right? So just make sure that we can close this Sim2Real gap in a pretty efficient manner. So this is basically how we are supporting, some of the world's best foundation model, robotics foundation model right now. So this example is with GR00T N1.5, which is NVIDIA's robotics foundation model. So you can see that for our teleops data, for our SimReady assets, we are supporting, the data collection as a major source. I would say as the most major source, and it would go through, the Mimi-Jan, the Cosmos, to augment the data and also combine with the real world data set and also human video sets in order to train the foundation model. But beyond that, after we enable our customer to get a foundation model, we would also leverage, the open source foundation model and also leveraging further synthetic data. So you can see on the left-hand side, which is the synthetic data we collect further through H1 from unit tree, right, by human teleoperation through the digital twin of a factory, right? And on the right-hand side is we actually Sim2Real the fine-tuned vision language action model through the GR00T N1.5 through our further synthetic data, and then deploy it in one of the world's largest, I would say, car manufacturing factory right now. Cool. And then basically, so I've been sharing a lot about, the SimReady asset part, right? The benchmarking, the data collection, and also how we are leveraging the data to do the Sim2Real, and also the best practices. And there's one more thing I want to mention, which I really see this is probably the most promising use cases of digital twins that we haven't seen much adoption yet, mainly because of we are at very, very early stage of this. But from our perspective, we are working with some of the world's most leading frontier labs to leverage this right now, which is the DeepSeek moment, right? The reinforcement learning fine-tuning moment of the large world model, the large robotics foundation model through digital twins. So this actually is putting even more requirements of digital twins, right? Meaning that it not only needs to be, visually accurate, but also physically accurate, but it's definitely not enough. You need to have a lot of diverse digital twins, but also you need to have a lot of tasks. And for the task, you also need to have some of the data collected, right? So that you can build in a very sparse reward. So meaning the SimReady digital twins, the tasks enabled, the diversity, right, and also the rewards, all need to set up. And then the other thing is the infrastructure side of the things there. Because I would say for the frontier labs there, they really have very good large-scale reinforcement learning infrastructure. But the part they don't have is the simulation infrastructure that can enable very efficient API to grab the digital twin, to grab the task, to grab the reward, right? So all those things are the things that we are currently working with some of the leading frontier labs right now, right? To enable them to do very large-scale RL fine-tuning of the digital twins. So this is an open source, I would say, framework that currently we are working with NVIDIA. So basically, from our side, it's called LW Lab. And from NVIDIA side, it's called SI Lab Arena. So this is really a simulated arena framework that can enable, the building of large-scale benchmark, the running of large-scale benchmark, the running of large-scale real-time data collection. And also, I would say the most important thing is the running of large-scale reinforcement large-scale reinforcement learning fine-tuning of the vision language action models. Cool. And if you are interested, we definitely love for you to reach out to us, and we would love to work with you on this direction. Yeah. In the end, I just want to say that I really appreciate this opportunity to give a talk about the awesome digital twins, and so really hope that we can work together to make the digital twins really awesome. Thank you.
So try again. Yeah. Hi, Steven. Yeah, thank you again for the great presentation. So, and I've seen like the digital assets you provided are really like photorealistic and seems like physical realistic. But like meanwhile, as people often like talk about like the Sim2Real gap. So in terms of the asset part, what can you see like what would be the like current challenge like between this like even if we have those assets, what would be challenged like in terms of the Sim2Real gap?
Thank you, Lei. So I would say this is really great point. So I would say there are definitely a few things which were challenges, but we solve it. So I would say for rigid body, for articulated, I would say the major gaps are already closed, right? In that, so there are a few gaps there. One is the visual gap, which we already closed. The other is the physical mechanism gap, right? So for example, if you can open up a fridge, right, and for the basic physical parameters, for example, the weight and other things that we already solved, and the articulation of the object we already solved. Then is the forces, the different type of forces, and we are leveraging the different type of force collector, right, in real, and also we have built all those sensors in Sim, right? We are marrying about the different type of I would say forces and benchmark them through the curve to close this gap. So I would say for the rigid body part, even including the articulated, we already closed the gap. The difficulty is more about scalability, right? In that we need large scale diversity of that. We are working on that, and I think it's pretty promising that we can close it very soon. The major reason there is we are also leveraging a lot of, I would say 3D generation model. And also we are leveraging a lot of large language model. And there is there is definitely some of the human in the loop but we can control that part pretty well. And also there's already good business model, right? In that we can close this gap pretty well. I would say the major challenge is still in the areas beyond rigid body. For example, deformable, for example, cable, for example, cloth, for example, the other type of fluid and other type of, I would say, assets. But I would say it's already pretty promising in that, for example, for cable, we actually solve it ourselves in that we leverage the work language provided by NVIDIA, which is a GPU accelerated language, right? We write cable software. We build on top of it the SimReady assets of cable. We leverage a lot of different type of measurement tools, working with the different type of labs, right, to collect the type of physical characters of the cable, and we input all of them into the simulated assets there, working with the solver itself, right, to solve it. So we don't solve the cable one, but there are a lot of different type of deformables that we haven't solved yet, right? And I would say in order for us to solve all those things there, we would strongly invite every great researcher to contribute together. So the major problem I see is people like to work in silos, right? In that, although a lot of researchers, you are working on the best paper, meaning, you are working on software, you are working on an asset, you are working on this Sim2Real, all by one paper, still it wouldn't contribute into an ecosystem, right? I would say the most important thing is for all of our work, it can contribute into one ecosystem. That is the most important thing. So that's why we are working with NVIDIA. We are supporting this open sourcing, I would say, ecosystem of simulation that includes, Deep Down, Newton, and then ICCV, ICCV, right? And we build a lot of things on them, right? And from a SimReady asset format perspective, we leverage OpenUSD format, right? All of those things can be open sourced. All of those things are already open sourced, right? So that meaning that if we add on more solvers, if we add on more assets there, we would all contribute into this ecosystem. And through this ecosystem, everyone would have the open source tooling to do the data collection, to do the benchmarking, and to do the reinforcement learning themselves, right? So this is the most beneficial way for everyone if you want to work on, I would say, more physically accurate deformables. The other thing there is, I really see this is also a very good way for everyone to magnify your impact through research, right? Meaning that the moment you finish this research paper, your work can already contribute into an industry-wide ecosystem that everyone can already use, right? So that is the most beauty part that I see. Yeah, thank you.
Yeah, like it's a crowdsourcing, just not just for the asset, but also for the part of the systems.
Exactly.
Thank you very much.
Thank you.